Hello, today we'll be talking about direction fields, also known as slope fields, and critical points of autonomous equations. So first off, we'll get into direction fields. What is a direction field and what does it tell us about our equation? So a direction field is when we plot the slope, slope of the solution of the differential equation at different points on the graph. And then from that, we can get an idea of what the particular solutions would look like, and it tells us more about our equation, for example. So here I have a table for the differential equation negative x over y. And when we plug in 0 and 1, we get 0 as our output. So at point 0, 1 on a graph, we'll put 0. Point 1, 1, we'll put negative 1. And likewise, we'll do this for many, many points for our differential equation. And from that, we can start to see what the solution of this differential equation could look like. So for example, here you see following the slope lines, it could look like this. And without an initial condition, there's many solutions. So the solution to this equation could look like this. And the more detailed it is, the more specific you could get from it. So critical points. What are critical points? Mathematically, critical points are when y prime equals 0. And these critical points can either be known as what is stable, unstable, or semi-stable. So here, 2 here is what's known as a stable point. That's because as t goes to infinity, the solution tends to go towards t. I mean, not t, towards 2. And here at negative 3, this is what's known as an unstable point because the solutions tend to go away from it. And between these critical points, you notice that the solution does not seem to pass. Like, they can never touch the critical points, they can only get asymptotically close. And here, 0, from here it looks like an unstable point, but when we go below the graph, we can see that the solution tends towards it. This is what's known as a semi-stable point. Now, we'll be looking to the specific equation y prime equals y times y minus 1 times y minus 3. So we know that equals 0 at 0, 1, and 3. We know that from algebra. And now we'll graph it with the vertical axis being y prime and the horizontal being y. And our equation will pass through our critical points. So here we can see, I've graphed that in Desmos the best I can. You can't actually have y prime as the vertical axis, but just stick with me here. And here we have critical points 0, 1, and 3. Now, we can find out which ones are stable and unstable from what's known as the arrows method. So we'll take a critical point, 3 for example, and so whenever the slope is positive, we'll draw a right arrow. When the slope is negative, we'll draw in a left arrow. And keep in mind this is the first derivative, so anything above the x-axis is positive, anything below is negative. So 3 to the right is positive, that's a right arrow. To the left, it's negative, left arrow. Critical point 1, the right, it's a negative slope, so that's a left arrow. And to the left, it's a positive slope, right arrow. And then we do the same thing for critical point 0. And now this lets us know which are stable and unstable. So critical point 3, the arrows point away, which means they're diverging away, which means it's unstable. Critical point 1, they're pointing in, converging to 1. It is a stable critical point. And 0 is also unstable. So from this, we can actually draw a conclusion. So here I've drawn this, and each horizontal line is one of our critical points. So a stable solution, that as t goes to infinity, they will tend towards it, and an unstable solution, as t goes to infinity, they will go away. And similarly, as t goes to negative infinity, it will go towards an unstable solution. So let's say we had a solution here. In this area, it would look like this. In this area, it would look like this. As you see, it's getting away from unstable and moving towards stable points. And same here, like that. And these are what solutions to this equation could look like. And to put that in perspective, I have this graphed out here. So as we see, when we're in this area between this unstable point and the stable one, it will tend towards 1, our stable point. And it will always tend towards 1, always go away from unstable points. Okay, so this has concluded my video over direction fields and critical points of autonomous equations. Thank you for watching.